Greetings and welcome to the pod. My name is Mark West. Now, what is the likelihood of a tsunami hitting your favourite beach? Dr. Hannah Power from the University of Newcastle's School of Environmental and Life Sciences conducts research on ocean waves and recently published on the likelihood and consequences of a tsunami hitting Sydney Harbour. She has also developed the risk forecast for the figure 8 pools in Sydney's Royal National Park. This forecast examines the likelihood of being struck by large waves on your journey across the rock shelf. I had a great chat to Hannah about her ocean wave modelling and started by asking her what really is the likelihood of a tsunami hitting the east coast of Australia.
Yeah, look, the risk varies depending on the size of the tsunami in the same way that it does for other natural hazards. So, for example, if you think about floods, the risk of a small flood is greater than the risk of a very large, very extensive flood. So the same goes for tsunami. So we can talk about the estimated return interval, which is the recurrence interval at which these events occur. And we might talk about, for example, a 1 in 100 year event. And that doesn't mean that the event happens regularly every 100 years. What it means that every year is that there's a 1 in 100 chance of that event occurring. So at the more frequent end of the return interval, we could say that we were exposed to small tsunami that have about a 1 in 25 year return interval. And the chance of experiencing a tsunami of that size in your lifetime is very, very high, but the size of the wave offshore of Sydney, for example, might be of the order of 5 centimetres. So the impact from an event like that is relatively small. If we go to the other end of the scale and look at sort of our worst realistic event that we could reasonably expect to happen, we might be up around the sort of 1 in 5,000 year return interval. And the chance of experiencing an event of that magnitude in a lifetime is around about 1 to 2%. But the size of that tsunami, instead of being 5 centimetres offshore of Sydney, might be of the order of about 1.4 metres. Now, you might think, oh, that's not very big because, 1.4 metres is about the average wave height that we get along most of the New South Wales coastline. But because of the way tsunami behave and because they have very long periods and very long wavelengths, a tsunami of 1.5 metres or 1.4 metres offshore of Sydney would have really extensive and really significant impacts.
So what's the real definition of a tsunami then? Like you see the movies and you see the 100-metre wall of waves coming in. I guess that might happen if an asteroid hits, but that's not normal. What's the definition of a tsunami?
No, well, so the word tsunami is a Japanese word, and it means harbour wave. So if you think about the ocean waves that are generated by wind that we see along the coast every day, they don't tend to propagate into harbours, whereas tsunami do, hence the name. So the majority of tsunami are caused by underwater earthquakes in ocean trenches. So as you mentioned, Australia is in the middle of a tectonic plate. We have a relatively low earthquake risk, and because all the ocean trenches that where most of the earthquakes around the globe happen are reasonably far away from us, that puts us sort of at a distance from that tsunami threat. So about, of the order of about 3/4 of tsunami are estimated to be caused by underwater earthquakes, where the earthquake occurs and it shifts the tectonic plates, and because the plates move and therefore the seafloor moves, the water column above moves, and that generates a wave that propagates outwards from the site of the earthquake. But as you mentioned, tsunami can be caused by other sources. So, for example, asteroids, which are rare. But the more common other sources aside from underwater earthquakes are things like submarine landslides, which can generate tsunami. You move a very large mass of the seafloor, and that movement of the seafloor generates a wave that again propagates outwards. Underwater volcanic eruptions. Alternatively, you could have volcanic eruptions or landslides above the water where material then slides into the water and generates a wave in that way.
And so what you mentioned they had a really long wavelength. What would they look like? Like if you were standing at Manly and saw a wave coming in, a tsunami coming in, what would it actually look like?
So if you were standing, for example, at Manly and you saw you were there and watching a very, very small tsunami, you probably wouldn't actually necessarily notice something. So, for example, the 2011 Japanese Tohoku tsunami that had devastating impacts in Japan was recorded at the tide gauge in Sydney Harbour, but you wouldn't have observed it if you were an observer standing on the harbour or standing along the coast because the impacts were very, very minimal. In contrast, if you were to experience a very large tsunami, so for example, our worst case scenario, which of course we wouldn't recommend, the emergency advice would say move away from the coast, go to high ground, and that's what we would of course advise everyone to do. But you may see the water retreat quite a distance. First, that may or may not happen. Alternatively, you may simply experience a mass of water moving onshore very quickly. And in the same way that a wind-generated wave has a part of that wave that runs up the beach and pushes water up the beach, the same thing would occur with a tsunami, but it would just simply keep on coming, and there would be more water in it for the very big events. So the periods for these things can be of the order of 10 minutes, so that means 10 minutes of onshore flow, and then 10 minutes of offshore flow.
Oh, wow.
Or of that sort of order of magnitude.
Okay. And how fast would it move?
So again, it depends on the size of the tsunami. For some of the smaller ones, we're talking of the order of 2 meters per second. That's about 4 knots. And while that might not sound like much, it is reasonably fast, particularly in areas of the harbour that are not normally exposed to very fast current speeds. To give a feel, it is about equivalent to the speed that an Olympic swimmer would swim at, and about a quarter of the speed of the Manly Ferry.
Right.
If we go up to some of our really dangerous events, we might see current speeds over 4 meters a second in some isolated places, up to even 10 meters a second in places. So if we were to see an event of that magnitude, it would have really significant impacts in the harbour.
Yes, you're unlikely to be swimming away from it, and probably unlikely to be running away from it, really, especially if it gets really shallow.
No, well, one of the things that we are lucky about in Australia is that, as you mentioned, we sit in the middle of a tectonic plate, so all those regions where the majority of tsunami are generated on those ocean trenches are far enough away that we're able to have a warning system that would give us of the order of about 1.5 hours warning for most of the Australian coast, if not longer. And so that's plenty of time to disseminate warnings and for people to respond to those warnings.
And what about tidal rivers? So I live near the Cooks River, but I guess the Parramatta River and Georges River and other rivers around the country, would they be affected by a tsunami? How far would it travel inland?
So again, it depends on the size of the tsunami. The biggest tsunami can travel further inland, and for the modelling we've done for the really big events, we see impacts all the way up Sydney Harbour, up Parramatta River, as far up to the end of the river as we've modelled. I can't recall the exact details of the Cooks River, but we do see that tsunami propagate up into estuaries, they propagate into harbours, they propagate into tidal rivers, and they also propagate into our tidal lakes for the very big events.
And this work, you've been doing some of this for the emergency services and the New South Wales Police designing their evacuation plan, is that right?
Well, we've done the underlying modelling. So we do the science of the sort of hazard assessment process. So we model a range of different tsunami events from very small tsunami, so more frequent events, up to very large tsunami, the less frequent events, and we map out things like the areas that we model to be inundated. We map out things like the current speeds. We also look at things like, for a given location, what the depth and current speed is, because that has a real impact for safety. You think about, you can probably stand up and not move in deep water that's not moving very fast, but you can't stand up in shallow water that is moving very fast. So we map out things like that as well. And then we provide that information to, for example, the New South Wales SES, State Emergency Services, and then they're able to use that to better inform their hazard mapping, their evacuation mapping, and then their planning around how they would respond in the event of a tsunami.
And so this kind of tsunami modelling falls under the greater concept of, I guess, coastal modelling. Is that right?
Yeah, absolutely, it does, yeah.
And because you're doing some really cool stuff for the figure eight pools in the Royal National Park, looking at exactly this, looking at the risk of being knocked over in shallow water down there. Is that right?
Yeah, so the figure eight pools is a really interesting site, and this is a project that I've worked with the New South Wales Office of Environment and Heritage on, and New South Wales Parks and Wildlife Services. And as I said, figure eight's an interesting site. It became sort of Instagram famous, you might say, a few years ago. Where
I did look it up, yeah.
Yeah, where they went from having sort of, of the order of a few thousand visitors across a whole summer to the site to having a few thousand visitors in a couple of weekends in a summer. So all of a sudden they had this problem to manage whereby they went from having people who were doing things like the coast walk in the Royal National Park, which is a long hike that you do, and most people who do it are sort of, people who are used to being outdoors, they're used to being out in the environment, they have an understanding of the risks, to having lots of international tourists and people who are perhaps not so familiar with being outdoors and what the risks of being in those, natural environments are. And so there was a really sharp increase in the number of major emergency incidents. So we had people being knocked over by waves and having head injuries, broken bones, and having to be evacuated out. And I perhaps should say that the figure eight pool is a rock platform. It's a horizontal rock platform along the coastline in the Royal National Park, and it sits between about 1 and 3 metres above the mean sea level. So that's about 0 to 2 to 3 metres above the high tide level. And so whenever we have waves, the waves break at the edge of this rock platform and they wash up and over the platform. And if they're big, they can knock people over. And this is what was happening. There's also a risk that you can be knocked over and washed off the platform and into the ocean. And so this became really problematic because it was a strain on emergency services. It's a very remote site. It takes about an hour and a half to walk there, an hour and a half to walk out. There's no road access. There's no boat access. If you can't walk out, you're getting helicoptered out, essentially. So there was this problem, and so I worked with colleagues at the Office of Environment and Heritage, and I had a couple of students from the University of Newcastle here work on this project as well, and we set up camera systems to monitor the platform and monitor the waves washing across the platform. And then what we did was we looked at that data, and we looked at, for all the data we collected about 8 months of data, and we looked at, for each hour of daylight that we had, we looked at how frequently the waves were washing over the platform and how far across the platform they were getting for each of those times that we had data for. And then we looked at that data and looked at data that told us what the wave height was offshore and what the tide level was, because as you can imagine, at higher tide, when the water level is higher, the risk of waves washing over the platform is higher. And so we were then able to essentially create a system that allows us to take the tide forecast and the wave forecast and relate it to a hazard level or a likelihood of waves washing over the platform. And that warning system that derived from that is now live on the Figure 8 website, and it provides, I think it's a 3-day forecast of what the hazard level is, what the risk is at that platform. Similar to how if you drive along the road outside of our cities, you might see a bushfire warning sign with those different colours and the arrow that goes around that semicircle. It's a similar kind of concept. So you can look at what the forecast is. It gives an hourly forecast for the period of time of the coming 3 to 4 days.
Yeah, that's cool. So right now it's low. the risk is low. So, well, nobody will be listening to this podcast as it's being recorded because it'll take me a while to edit it. But
Sure.
right now it's low. It's very interesting. So, do you have plans, or do the national parks have plans to expand this to other similar places?
Look, the methodology that we developed could be expanded to other places, but the risk forecast tool that we developed for this site is site-specific. So the figure 8 pools has some interesting morphology. It's orientated in a particular direction, so that orientation relative to the direction that the waves are coming in from makes a difference as to what the risk rating is. And so the tool isn't directly transferable to other sites. But we could certainly take the methodology and apply it to different sites if there was a similar kind of need to develop such a tool.
Yeah, you could imagine it for surfers jumping off the rocks at Bondi or wherever, can't you? Like you can sort of see how
absolutely.
it would work. Yeah. And is it the same sort of modelling? You do a bit of work in coastal erosion, looking at where we can build up to on the coast and the reduction of sand on beaches and that sort of thing. Is this the same sort of work, or is it a bit different?
So it's a little bit different. That's not work that I'm directly involved in, but it's work that I've got a lot of colleagues who do. And so that kind of work looks more at longer term processes. So with the risk forecast tool for figure 8, even one single wave, if we observe the coastline for a 20-minute period, one single wave can be really, really problematic and can change your risk rating from low to extreme because it just takes one wave to knock you over. With the long-term coastal modelling and coastal erosion work that's being done for New South Wales, for example, we're looking at how the coast is likely to change in the future based on things like sea level rise. So what we do is we look at how much erosion we might experience at different return intervals. So this goes back to that concept that I talked about with regards to tsunami, how frequent, in this case, storms are. We look at how much erosion you might get from a particular storm, and then we combine that with the erosion that we would expect to see due to sea level rise. And from there, we're able to forecast where the shoreline might be for different probabilities going into the future.
Okay, that's really interesting because I imagine that not just sea level rise, but just the change in climate, more storms presumably will have a big effect on this sort of thing.
Yeah, so all of those things have a big effect, but as you might be aware, there's also a lot of uncertainty around these things. So, for example, sea level rise, we know that the sea level is rising, but being able to forecast where the sea level will be at, say, 2100 is challenging. And so there's a lot of uncertainty around that. There's also a lot of uncertainty around what we do, how much we reduce our carbon emissions, which has flow-on effects to what the sea level will do.
Yep.
And so it's really important that all of those uncertainties get incorporated into the modelling. And the way that we do that is we run our model lots and lots and lots and lots of times with different sea levels within our range of what we expect them to be, and then we combine all those results to get a probability. So we can then say, well, there's a 50% chance that the shoreline will be at this position or further landward at this time.
And so what's next for your work, apart from presumably spending more time at the beach? What's next?
Yeah, so I've recently found out that myself and some colleagues from the University of Sydney have been awarded some time on the Marine National Facility, which is our premier marine research vessel that's run by the CSIRO. Cool. And so in July next year, we'll be heading to sea for 11 days to do some mapping and collect some samples from some of the submarine landslides that exist off the East Australian coast. So we'll be going from Cairns to Hobart, we'll be mapping the slides or mapping parts of the slides that have yet to be mapped, and also collecting some sediment data, which we might use to, for example, date when these submarine landslides occurred, to get a better feel for how frequently they occur. And also all these data will allow us to better model what the potential impacts would be should we have a submarine landslide occur in the future that generates a tsunami.
Cairns to Hobart. That's an amazing trip. You're going to see some different sea conditions, I think.
We will, yeah.
And I imagine those landslides are in the same way we were talking about being able to predict a single wave. I guess predicting a single landslide might be quite difficult, but this would tell you something about the rate they've occurred over the last X number of years, I guess.
Yeah, exactly. So in the data that we have, in the mapping that we have of our seafloor off the East Australian coast, we can see a few different things. We can see submarine landslide scars, so these sort of sections that have been carved out of the seafloor that tell us where previous submarine landslides have occurred. So that allows us to at least understand what the largest realistic slide that we could experience could be. And they're very big features. They're over 10 kilometres long in places and 5 to 10 kilometres wide in places. So we're talking really big amounts of material. The other thing that we can see in the seafloor mapping is areas of our continental slope where we see cracks in the seafloor. And we can actually see, and this is in the sediment that sits on top of the underlying rock that makes up our continent, and we can see these cracks that are tension cracks, and they sort of suggest that that material is unstable and might potentially slide into the future. So we can identify our scars, so our past submarine landslides. We can identify sites where we think there will likely be a future submarine landslide. And then, of course, there's the potential that it could happen anywhere along the coast where we don't see these cracks. Luckily for us, they seem to be reasonably infrequent events, of the order of 1 in every 5,000 to 1 in every 15,000 years.
Okay.
So the risk is relatively small. The difference between a tsunami generated by a submarine landslide and a tsunami generated by an earthquake for the east coast of Australia is that the warning system that we have wouldn't pick up on a submarine landslide generated tsunami, and the time between landsliding occurring and the tsunami reaching the coast is significantly shorter for submarine landslide generated tsunami. It's of the order of about 15 to 20 minutes.
Okay. How come it wouldn't get picked up? Is it too close to the coastline?
It's because the way our warning system works, it's focused on earthquake generated tsunami. So the warning system that we have in Australia, which is jointly run by Geoscience Australia and the Bureau of Meteorology, identifies earthquakes. It identifies where the earthquake has occurred, and if it's an earthquake on land, then there's no tsunami risk. If it's underwater, they look at the size of it, how deep in the crust it was, and assess those factors to determine if it has the potential to generate a tsunami.
Okay.
And then from there, we use a sort of back catalogue of modelled tsunamis for different size and location earthquakes, and then identify what the risk is based on that. And then those warnings are further fine-tuned based on observations from buoys that are located around Australia that pick up tsunami waves. Now, they're in really deep water, and their primary purpose is to identify earthquake-generated tsunami waves. So the system that we have set up isn't set up to identify tsunami from submarine landslides.
Okay.
Having said that, at this stage, our hypothesis is that the most likely trigger for a big submarine landslide is a big earthquake. And so if we had a really big earthquake on the east coast of Australia, our advice would be that there's the potential for a tsunami to happen. And if you're located in low-lying coastal land, we would recommend that you move to higher ground and further away from the coast.
Cette bestiole horrible courait devant moi alors que je t'avais demandé de désaffecter. Cette maison est infestée par la vermine. On n'y trouve que sur une soluble.
Is the east coast where Australia is more likely to get hit by a tsunami, or is it more likely up in the north, closer to Japan or Indonesia, places where there have been earthquakes of recent times?
Yeah, so the areas around Australia that are sort of most at risk of tsunami are the east coast has a reasonable risk, and then the northwest coast of Australia, so northern Western Australia. So that part of Australia is exposed to tsunami generated by the Sunda Trench and the Java Trench along the Indonesian, adjacent to the Indonesian coastline, and that's where the Boxing Day tsunami was generated from. And we did experience impacts in Western Australia from that tsunami. And then the east coast of Australia, because we face the Pacific Ocean, which is where the majority of earthquakes globally happen, we're exposed to tsunami generated by, for example, the ocean trenches off Japan, but also the ocean trenches off Chile and South America. And for example, the most impactful tsunami that we have photographic and data records for Sydney was the Chile 1960 tsunami. So it was a tsunami generated off Chile. It was a 9.2 magnitude earthquake, which is an absolutely enormous earthquake. And it was recorded in Sydney Harbour. Observers identified very high current speeds at Spit Bridge and Anzac Bridge, so these are places well within the harbour. There were some vessels sunk within the harbour. About 30 ships were pulled off their moorings at Spit Bridge, and there was some significant erosion at Clontarf within the harbour because of those very fast current speeds.
That's amazing because it's thousands of kilometres away, isn't it?
Absolutely. We would have a very long warning time if there was a big event off Chile, again, that generated a tsunami, because it takes time for that wave to travel here. But to give you a feel, the recorded wave height, the maximum wave height recorded from that tsunami at Fort Denison tide gauge within Sydney Harbour was 80 centimetres.
Okay. I guess it's just such an amazing volume of water that would come in, wouldn't it?
Exactly, and that's the big challenge, is that you've got a huge volume of water flowing in for an extended period of time, as I said, maybe 5, 10, 15 minutes, and then that all turns around and flows back out again.
Yeah, that'd be, well, you hope you never have to see it, but it would be amazing.
Absolutely, yeah. And one of the things that we've done here at the University of Newcastle to give people a bit of a feel of what it's like is we worked with our digital innovation team to generate a sort of virtual reality video of what a tsunami might look like we modelled a sort of fictitious harbour, and you can see the boats moving up and down, and we modelled a fairly sort of small scale tsunami, so something that we might reasonably expect to see within our lifetime, and you see boats being pulled from moorings and sort of shunted around in the harbour, and it gives people a bit of an idea of what a tsunami might look like.
How do you get the sediment off the bottom of the ocean? It's pretty deep there. Have you got some uninhabited vehicles that you're sending down?
So it is pretty deep, you're right. Depending on where you're collecting sediment from, off the east coast of Australia, you might get down to about 4 kilometres depth. So the facilities and the equipment on the Marine National Facility allows us to deploy instruments. We sort of winch them down essentially, and you might have something called a grab that looks a bit like a bird's beak, and you lower it down open to the sea floor, and it triggers when it hits the sea floor, and the beak closes and it collects some sediment, and you winch it back up to the boat.
Wow. That's
so
a lot of
you
cable.
might. It's a lot of cable. And it's a lot of waiting around because it might take 40 minutes, an hour to get down to the bottom, depending on what depth you're in. And then it takes that same amount of time to come back up again. So it's a lot of waiting around, but there's also a lot of excitement when you do get that sediment back on board.
Yeah. Is it immediately obvious if it's kind of really cool? Like, it's not going to come out fluorescent green or something like that, but I guess to the trained eye, you'll know what you're looking at.
It can be. So, for example, one of the things that we hope to do on this trip is collect some sediment cores. So these are essentially, if you think about like a really long drain pipe, you might try to get 5, 6 or more meters of core, and you lower it's like a drain pipe, down to the bottom of the ocean. And depending on the system you use, one example might be you just have a really large weight at the top, and you lower it right down to just above the seafloor, and then when your core barrel is just above the seafloor, you essentially let go of the winch and the weight drives that barrel into the seafloor, collects, hopefully, a full core of sediment, and then what you do is you get it back on board, you cut it up into sections, normally metre-long sections, and you can split them in half. And for example, if we were to do that through a submarine landslide scar, what we would hope to see is a really clear and defined boundary at one point in that core where you might see a really distinctive colour change or a really distinctive change in grain size. So, for example, from mud to sand, that would tell you that you've identified the surface of that slide from when it happened. And then the sediment above that change or that boundary would be sediment that's been deposited on top of that scar since that slide occurred. And the idea would be that you would date the sediment just above that boundary feature, and that would give you the timing of when that slide occurred. Yeah. So yeah, you can at times immediately see that you have something really exciting and really cool in your sediment.
Yeah, it must be quite soft or the weight really heavy then, I guess, for it to plummet, 6 metres through the ground.
Yeah, the weight's really heavy because the sediment gets quite compacted because it's a lot of very fine muds and silts, and it can be very, very old. So, tens of thousands of years old, and over time, all of that, you can imagine it's been really compacted down.
Is the top layer kind of obviously impacted by humans, or are we far enough? Are we kind of in the wilderness enough that that's not clear?
No, there's pretty clear scientific evidence that in most sediment cores around the globe, we can identify the point at which we see anthropogenic impacts. The other thing that surprised me the first time I ever went to sea, and we were about 300 nautical miles northeast of Lord Howe Island, so really in a fairly remote location, and we were doing underwater video tows, so we were towing a video camera a couple of metres above the seafloor, and we had a live feed to the ship, and one of the things that really shocked me was that we saw rubbish on the seafloor.
That's depressing.
Yeah, and you think, you're in this exceptionally, well, at least you're a really long way away from, big cities, big communities. The nearest place is Lord Howe Island. That's a really, really small, population there. Yep. And yet, you're looking at this video feed that's coming from 3,000 meters depth. You're seeing, an area of about probably 2 meters by 3 meters or thereabouts, and you're moving at a speed of, about 4 kilometers an hour, and you're doing it for an hour. So you're really not seeing a very large area, but to see rubbish in that gives you a sort of feel for the impact that we have had and the widespread nature of that impact.
Well, that's all the time we have in this edition of the pod. Thank you very much to Dr. Hannah Power from the University of Newcastle for taking the time to chat tsunamis and ocean wave modelling. If you'd like any more information on anything you've heard today, get over to the website at www.thepodpodcast.net. That's www.thepodpodcast.net. And there you can find links to Hannah's work and all the songs you heard in this episode. Thanks for tuning in. My name's Mark West. I'll catch you next time on the pod.